Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. We are discussing about aquatic chemistry and water pollution. The previous class we discussed about the general importance of water and some of the various reactions. In brief, we discussed what is happening in water or aquatic media. And this lecture class we are going to discuss about solubility of various chemical substances in water and the theory behind it. Usually a substance is soluble in water, and this is considered as a solubility. That is, the concentration of a chemical substance in the saturated solution is usually called solubility. The previous lecture itself I mentioned water is a universal solvent, and for this to happen, important thing is its polarity. It's a dipolar compound. So, any polar chemical likes to dissolve in water, and solubilities of different substances in water vary enormously. Again, depends on its nature. Usually like polar compounds like to dissolve in water very much. A solution that has dissolved as much as solute is possible is to be saturated with regard to that particular chemical solute. And sometime we will encounter supersaturated solution. That is possible. That is beyond the capacity of saturation. Consider the well known example of Coke, Pepsi or soda water. And usually what we do is we carbonate this beverages bottle at an elevated temperature. When we open, carbon dioxide gas will come out. Okay. When we remove the cap, with a sound also, with a loud pop sound. Why it is happening is because in this bottled water usually carbon dioxide is filled under supersaturated condition, that is beyond the solubility capacity, and this is happening because by passing water under cold condition, under pressure carbon dioxide becomes supersaturated soluble in water. So, this is the main reason. At cold condition nothing will happen, but in the ambient condition, if you open the supersaturated solution, carbon dioxide present in the solution will come out. That is, it relieves the supersaturation to saturation limit, because at a warmer condition its solubility decreases, whereas cold condition gas usually solubilize more. This is the one. So, what are the factors affecting solubility? With respect to gases, two factors affect solubility. One is the temperature and pressure. Okay. As I told you in the carbon dioxide example, under high pressure and cold temperature, carbon dioxide in water becomes supersaturated solution. Usually gases are soluble in water too, but it is governed by the Henry's popular law, and he described the solubility of different gases in water, and according to this, the Henry's law states at constant temperature the solubility of a gas in liquid is proportional to the partial pressure of the gas in contact with the particular liquid. Usually here it is water. Suppose for a gas, let us say X, this law applicable to equilibrium type again with this gas in water. Okay. That is, the concentration of the particular gaseous solute in aqueous medium is proportional to concentration. The proportionality is removed by a constant, gas constant, that is Henry's constant K, and this is a mathematical form of this Henry's equation. But this does not hold good for any chemical species, gaseous chemical species, undergo reaction in water due to the acid base nature. For example, you consider ammonia. If it is solubilized in water, it gets converted into ammonium and hydroxide ion. And similarly, sulfur dioxide, if it reacts with a bicarbonate water, and here the bicarbonate reacts with this sulfur dioxide, gets converted to bisulfite and carbon dioxide. So, under these type of, if there is a new species formed, and usually the chemical reactions does not hold good. And this table gives you some idea about Henry's law constant for some of the gases, and water at 25 degrees Celsius, oxygen is having 1.28 into 10 power minus 3, carbon dioxide 3.36 into 10 power minus 2. Similarly, hydrogen is also to some extent soluble, methane, nitrogen, NO, but the solubilities are very, very poor. Two things are very important with respect to gases. One is oxygen in water, the other one is carbon dioxide. So, we will see some little more information about the solubility of oxygen and carbon dioxide in water. Oxygen that dissolved in water comes from usually atmosphere, because the aquatic system is in direct contact with the atmosphere, where it is 21% is available, and due to this oxygen gets solubilized in water. And also from photosynthetic action of algae, usually they liberate oxygen, that also provide oxygen to aquatic system. And this oxygen in water is essential for both fish and other organisms living in the aquatic system for their survival. And as many kinds of aquatic organisms require oxygen for their existence, water bodies should contain appreciable level of dissolved oxygen, usually above 4 milligram per liter is considered to be good. Then only the water body will remain a healthy water body. And suppose in aquatic system organic matter are present, usually from natural things like vegetation decays, leaves and wood and other things. If organic matter is released into the water, that consume dissolved oxygen, and the ability of a body of water to reoxygenate itself by contact with the atmosphere is an important characteristic, and this may be a problem under reoxygenate conditions, because the organic matter hindrance to this. Okay. And such kind of organic matters are present in high amount, usually in the water bodies will have with the DO value, dissolved oxygen value, less than 2 milligram per liter, and that indication something contamination or the water body is polluted. So, for a healthy aquatic water body, the dissolved oxygen level should be above 4. Next important chemical species in water due to solubility is carbon dioxide gas. Okay. And this is very important for photosynthesis of algae material in water. They with the light sunlight they convert this, as well as the carbon dioxide dissolved in water bodies act as a natural buffer, provides natural buffer capacity for the aquatic system. So, in these two ways carbon dioxide solubility in water is very, very important. Let us see some salient features of this. Carbon dioxide and water, if it is dissolved, usually being a weak acid, it undergoes a decomposition to form bicarbonate anion and H plus. Okay. And the chemical equilibrium equations can be written for this also, and this dissociation constant value for this one is 4.45 into 10 power minus 7, that is the pKa value. If we write it is 6.35, and this bicarbonate can further undergo loose proton becomes carbonate anion again, CO3 2 minus plus H plus, and the chemical equilibrium equation can be written for this equation also in this way, and this is a equilibrium constant value, and the pKa2 is 10.33. Okay. So, this is bicarbonate to carbonate conversion will take place above this equations. Okay. So, these two values are important, 6.35 and 10.33. How the species variation will take place can be explained based on this pKa 1 and 2 value. And this is a species distribution diagram as per the above pKa 1 and pKa 2, and these are the concentration of species, and the pH value in the x axis is plotted. You can see here, as the pH value increases, what happens is CO2 is present, free carbon dioxide is present till this 6.33. Beyond this, this is converted into bicarbonate ion. So, up to this it is present as a bicarbonate. Beyond this 10.33, the bicarbonate will be converted to carbonate anion. And you can see the diagram, all these three species will not coexist at any given condition, only maximum 2 species possible. Either free carbon dioxide and bicarbonate is possible, or bicarbonate and carbonate is possible. Never carbonate with carbon dioxide is possible. The moment such condition exists, immediately the carbon dioxide will be converted to bicarbonate, vice versa, like this. So, the distribution of species concentration, if you want to find out, can be applied this chemical equilibrium equation, and you can find what are the amount of free carbon dioxide, what are the fraction of bicarbonate, and what are the fraction of carbonate can be find out using the chemical equilibrium equation as we seen before. And if you see the atmospheric free concentration, that also provides solubility in water. We have seen due to burning of fuels, whatever we emit, about, let us assume 350 ppm of carbon dioxide is present, and that is equivalent to 1.146 into 10 power minus 5 moles per liter of equivalent to carbon dioxide. Okay. So, 350 ppm. Okay. This is a concentration that comes through. Suppose the concentration is this much. Now, the current concentration is 410 ppm. So, this value is still, the H plus ion concentration is still much more. So, the carbon dioxide dissociate partly in water to produce equal concentration of H plus and bicarbonate, being a weak acid. So, these equations what we have seen before, all this one, carbon dioxide dissolves in water, forms bicarbonate, this undergoes further dissociation to form carbonate, etc. And if we substitute the pKa 1 value, pKa 2 values, all this in this equation, the above equation, we can see the pH of the solution will come to 5.65. The above concentration of this value, if you put it in this equilibrium equations, and this is a pKa 1, pKa 2, if you work out this value, it comes to, that is the 350 ppm carbon dioxide will provide a pH value of 5.65. Okay. That is what we have discussed earlier during acid rain also. pH value up to this is considered to be normal, below pH 5.65 only it was considered as a acid rain. So, the above calculation clearly says why the pure water that is equilibrated to the unpolluted atmosphere is slightly acidic, because 5.65 indicates some of the carbon dioxide present in the atmosphere gets solubilized and pH is reduced to 5.65 from 7 from the neutral value. Suppose the same water, if we aerate it, what will happen? If we pass pure air or purge the air, and if you measure, the pH value again will come to towards 7, because some of the dissolved carbon dioxide during aeration might have escaped the solution, and this accounts for increase in pH. So, the increased solubility of carbon dioxide in water and elevated alkali also possible, that is because of this reaction conversion. Carbon dioxide will react with the alkalinity of OH and gets converted into bicarbonate. This accounts for higher solubility of carbon dioxide in alkaline water, because carbon dioxide is converted into bicarbonate as per this chemical equations. So, carbon dioxide solubility depends on not only pressure and temperature, its alkalinity also. So, aerated water usually close to 7, whereas atmospheric equilibrated water, the pH will be slightly acidic. Similarly, the solubility of liquid in water is also possible and depends on what is the nature of the solid. For example, if we consider alcohol, methanol, ethanol or isopropyl alcohol, all these alcohols freely water soluble. At the same time, if you take benzene or any oil type of things, their solubility in water is very, very poor. Okay. So, it depends on what is the nature of this particular liquid substance, polar or non-polar, that determines the solubility of that particular liquid in water. Now, we will move on to solubility of solid chemical substances in water, that is more important. Generally, the solubility of solid in water is of concern when a solid is slightly soluble or often having such a low solubility that is called insoluble, because some of the toxic materials maybe becomes sparingly soluble or insoluble. Just consider the solubility of lead carbonate in water. Okay. The lead carbonate, which is usually insoluble in water, slightly soluble or sparingly soluble, dissociate form lead anion and carbonate, lead 2 plus and carbonate anion. So, through this solubility reaction, it can bring toxicity to the water. Even though the original compound is lead carbonate, it has ability to dissolve in water to a slight extent that is good enough to cause toxicity to the water. So, we have to understand, to explain the solubility of these sparingly soluble compounds, what is important is we have to understand this solubility concept principle again, KSP. Consider this barium sulphate again will undergo dissociation to form barium 2 plus ion and sulphate anion, and this can be written in the equilibrium constant KSP is equivalent to barium ion into sulphate divided by undissociated barium. Usually the concentration is taken as unity, that is equivalent to 1.23 into 10 power minus 10, that is a KSP value composition. So, solubility of sparingly soluble compounds can be explained based on the solubility product concept, normally represented by KSP equilibrium concept. In the simplest cases, the solubility product can be used to explain and to calculate the solubility of slightly soluble salt in water. Okay. So, just consider this again barium sulphate if soluble furnish equal amount of barium 2 plus and sulphate anion, that is called its solubility. Using the concept of solubility product KSP, this equation, if we find the solubility of this barium sulphate in water comes to 1.1 into 10 power minus 5 moles per liter. Using this KSP value, if you solve this, this is the value. So, like this, any insoluble compound can be explained with the help of KSP value. And this slide summarizes some of the sparingly soluble compounds that's used in to various environmental applications, to precipitate heavy metal or hardness removal, etc., as calcium carbonate or magnesium, etc., can be explained based on the insoluble compound. For each one, their solubility constant value is important, KSP value. Let us see how it is happening. And some more compounds including iron, coagulation, iron removal, manganese removal, aluminum, all these wherever toxic components are there, if you want to remove this by converting into the insoluble compound, again this KSP value will be very, very useful. So, just I will take one example, because heavy metals are important environmental contaminant. It comes from many industrial waste stream, ultimately pollute many river water bodies. So, it is very, very important to remove the heavy metals present in the industrial effluent. One such type of treatment method used is through chemical precipitation. What is this? That is, soluble contaminants are converted to insoluble forms by chemical reactants or by change in the composition of the thing. So, any heavy metals under favorable conditions can be converted into insoluble form, that is normally known as chemical precipitation. To understand this, the KSP value, solubility product concept, is very useful. Especially dissolved toxic metal may be precipitated from the aqueous solution mainly through three routes. One is as a hydroxy precipitate, sulfide precipitate, or sometimes as a carbonate also. Of course, the predominant one is hydroxide. Okay. That is, a substance gets precipitated when the ionic product, that is the product of the ions present in a solution, exceeds the value of the solubility product of the substance. So, the equation is given here, and the KSP value is a key for this. And for most of the metal, especially the toxic heavy metal present in wastewater or industrial effluent, can be precipitated as a respective hydroxide by raising the pH alone between 9 to 11. Most of the metal can be precipitated by adding either sodium hydroxide or lime, that is calcium hydroxide, or sometimes magnesium hydroxide. We can add this to raise the pH between 9 to 11. Most of the heavy metals will be precipitated out, and then these precipitated metals will be removed by settling and or filtration. And this slide show you the various heavy metal normally present in industries like electroplating or mining, all this. Ultimately, before discharge, these effluent containing these toxic heavy metal should be removed, and the corresponding metal hydroxide or sulfide or carbonate. You can see here mostly it's all can be removed as their hydroxide, or very rarely as a sulfide, and sometimes again carbonate. And for this, the logic is the value here. The more negative value is the one, that means it is very least soluble. So, you have to see the KSP value of the particular metal hydroxide, sulfide or carbonate, and then you have to select. You just consider the mercury. If you go for hydroxide, you cannot completely remove all the mercury, and it is very difficult to meet the discharge limit. And then consider the sulfide, it is minus 56, it is almost double. So, mercury usually precipitated as a mercury sulfide, okay, rather than hydroxide, or two stage precipitation, first initially by hydroxide and the second stage by sulfide. So, the KSP value is very useful when you want to precipitate or remove certain metals, toxic metal from the industrial effluent. The KSP value is very handy. And as I told you, hydroxide precipitation is the one mainly used for the removal of most of the toxic metals present, and usually precipitated between 10.5 to 11 or something, or usually in the alkaline with the help of precipitating agents like caustic soda, lime or magnesium hydroxide. This slide shows the precipitation of different metals at a different pH and the residual metal concentration. And you can see here each metal gets precipitated at different pH, ion solubility curve, and this is a chromium, cadmium, and this is zinc, copper, and each metal gets precipitated in a different pH. This is what is a main concern, because very difficult to have a common precipitate, because some have solubility at 7.5 to 8, other metal have 10.5 to 11. This makes this process a little cumbersome, so very difficult. So, you have to see this value and what are the metal present in the particular situation. Either you have to go for, conditions are favorable, you can go for this, otherwise separate metal precipitation is ideal. In the previous diagram also you might have noticed chromium, you see the solubility curve comes down, reaches minimum, and again going back. Similarly, zinc, see the curve for zinc, comes down, and this is a minimum. Again the pH is not controlled properly, again rises back. This is a solubility pH normally we have to maintain, okay. And this is a pH usually we have to maintain for chromium if you want to remove. It is close to 8, whereas zinc it is close to 11. So this is a complication with this hydroxide precipitation system. If it is a single metal, yes, fine, we can select the appropriate pH, the solubility minimum curve, and you can proceed with this. So these two metals, chromium and zinc, are called amphoteric because of the minimum solubility here, and we have to go for this. And this is again amphoteric hydroxide is very important for water treatment. Aluminum also a amphoteric metal. So the metals like chromium, aluminum, zinc, all this have soluble in both acid medium and alkaline medium, because just to see the equations for aluminum 3, if you add the hydroxide, it will initially form this soluble. Next, if you add more hydroxide, this is again positively charged soluble. If you add 3 moles and all the 3 aluminum is neutralized, you have aluminum hydroxide. This is insoluble species because no charge here, so it is insoluble. From water it precipitated. Suppose aluminum, if you add very little hydroxide, if this species are present positively charged, water soluble. And again if you add more amount of hydroxide, what happens? The aluminum hydroxide goes into solution again, aluminite with the anion here, again negative charge. This is also water soluble. So this clearly explains the amphoteric nature of aluminum 3. So the pH, if you want to have minimum aluminum, this is the pH condition you have to use it. Same thing with chromium 3, close to 8, zinc maybe 11. So we have to control the pH if these type of amphoteric metals are present, otherwise residual concentration of this metal will be high. So to sum up about the solubility of different chemical species in water, we have discussed the solubility of gases like carbon dioxide and oxygen. These two are very important. Oxygen is survival for any aquatic system including fish. A good dissolved oxygen content should be present above 4, that makes it life very easy. Similarly, carbon dioxide also should be present in water, and that helps in photosynthesis process, especially at the same time provides oxygen also. So we discussed how the different chemical species of carbon dioxide soluble one at a different pH condition, that explain the buffering capacity of water body system. So carbonate, bicarbonate, free carbon dioxide is a naturally occurring buffer system which holds buffering capacity. And next we discuss about solid material, amphoteric, metal hydroxide, metal hydroxide, metal carbonate, metal sulfide. This is very important. Whenever some industries they are going for removal of this toxic metal, they have to pay attention to pH and the KSP value. If you pay proper or control the proper pH and pay attention to the solubility, definitely we can minimize the discharge of toxic heavy metal into the aquatic system, thereby we protect the aquatic system without any harmful effect of that. Thank you.